Okay, here we go with another series of MAP 2302 video lectures. I don't know if you can hear them, but I brought the birds back by popular demand, so they're there in the background, whether you can hear them or not. Maybe right now they're not being too loud, but at some point they'll start making their noises. Well, now that I started recording, they're keeping quiet. Okay, so we're going to start here with section 7.6, the transforms of discontinuous functions. So the first thing we need to do is define one particular discontinuous function called the unit step function. We will always use here in this part of the book u of t to denote the unit step function. It's the function which is defined as 0 if t is negative and 1 if t is positive. Okay, so the graph, it's 0 here and 1 here, and it is not defined at t equals 0. Now, if we have some other step function, maybe the jump is at a different location, say the jump, instead of being at t equals 0, the jump is at t equals a, we can get that using the unit step function by simply looking at u of t minus a, because this thing is going to be 0 if t is less than a, and 1 if t is bigger than a. So if you look at u of t minus a, that graph is going to have a jump at a. Now, if we had a jump of a different size, instead of jumping 1 unit, maybe it jumped m units. Well, then we can just multiply that previous function by m. So m times u of t minus a is going to be 0 if t is less than a, and it's going to be m if t is greater than a. So there's a, 0, m. So we can make our jump have any size and have it occur anywhere by manipulating this unit step function. Another thing that we can do with our unit step function is we can make something called a window function. So the window function, our notation for that is capital Pi sub ab of t, and it's defined to be u of t minus a minus u of t minus b. And if we work out what that is piecewise, we can think, well, first of all, if t is less than a, so here we want to be thinking of a is less than b. These are constants, a and b are constants, and a is the smaller one. So if t is less than a, then both t minus a and t minus b, they're both negative. So both of the terms there in the definition are 0. So this thing is 0 if t is less than a. Now, if t is between a and b, then t minus a is positive, but t minus b is negative, so that thing becomes 1 minus 0. So this thing is 1 if t is between a and b. And then if t is bigger than b, then both of them, both t minus a and t minus b, are both positive, so the expression is 1 minus 1, and so again it's 0. And if we graph that, here's a, here's b, it's 0 to the left of a, 0 to the right of b, and it's 1 in between. So it's 1 precisely on this window, this interval from a to b. And what we can do with the window function is, one thing we can do is the following. So let's say that I have a function defined on the whole real line, f of t. Now, if I take f of t and multiply it by my window function, so f of t times pi sub ab of t, what's the effect? Well, between a and b, the window function is 1. So between a and b, it doesn't do anything to my function. My function remains the same. Try and draw it similar. But outside the interval a, b, the window function is 0, and so it kills my original function. And we'll see later, as we work with these things, why that's important and how doing that can be helpful to us. Scroll back down, you can see all that on one screen. Well, can't quite see all of it. Okay, let's do an example. Okay, so let's, in this example, we want to write the following function using step and window functions. So the function in the example is defined as f of t equals 3 if t is less than 2. It's 1 if t is between 2 and 5. It's t if t is between 5 and 8. And it's t squared over 10 if t is bigger than 8. And we want to write this function using step and window functions. Okay? Well, we can there's not a lot of work to show. You can pretty much just read it right off of the definition. So, first of all, I've got a window. Now, this is for t positive here. Maybe I should put this. Well, I could put this is for t positive. Okay. So I have a window, the first line in the definition of f, I've got a window from 0 to 2. And on that window, my function is equal to 3. So I could begin by writing 3 times the window function from 0 to 2 of t. Okay, that gives me the first line, and if I stopped there, then the function would just be 3 on that window, it would be 0 everywhere else. All right, well, okay, so I want it now to be 1 on the window from 2 to 5. So let's add 1 times the window from 2 to 5. And now we see if t is between 0 and 2, it's the second term that's 0 and is not contributing. Whereas if t is between 2 and 5, it's the first term that's 0 and is not contributing. And we just continue like this. So we can put plus t times the window from 5 to 8 plus t squared over 10 times what? Well, now it's not really a window, or we don't call it a window, because it's going from 8 all the way to infinity. So there we use the unit step function, the one that jumps up to 1 at the point 8. So I want u of t minus 8. And what we've done in this example is we've taken a piecewise function, or a function that's defined piecewise, and we've defined it in a single line. And that's a tremendously helpful thing to be able to do. Because, well, when something's written piecewise and you want to do an operation on it, then you have to think separately and do that operation on all the different pieces. Whereas now the way we've written it here, it's one single formula or expression for our function f, and we'll be able to operate on that thing as a whole without having to go separately down a list of different cases. Now, one of the things that we're going to do is, of course, it's chapter 7, we're going to be doing things with the Laplace transform. So the Laplace transform of the unit step function, well, when you're doing the Laplace transform, you're just integrating from 0 to infinity. So you don't care what your function looks like or if it's even defined when t is negative. So when the Laplace transform looks at u of t, it can't tell any difference between u of t and just the constant function 1. So this is the same as the Laplace transform of 1, which is 1 over s, as we saw before. Okay. Now the Laplace transform of a shifted unit step function, now that's a different story. So let's work that out from the definition of the Laplace transform. So we're going to take the integral from 0 to infinity of e to the negative st times u of t minus a dt. Now u of t minus a, this is the function that is 0 up until you reach a, and then it jumps up to 1 at a and it stays 1 after that. So when you're integrating, as t goes from 0 to a, that part is just 0. And you only then have to worry about integrating from a to infinity. And at that point, once you're on the interval from a to infinity, the function u of t minus a is just 1, so you can just get rid of it, and we end up with this integral. And then we do this calculus, this integration, and we end up with e to the negative as over s, valid for s positive. So that's the Laplace transform of a shifted unit step function. So that's two rules that we're going to want to use as we start doing things in this section. There's one more rule that we want to talk about. What happens if I want to do the Laplace transform of, say, a function f evaluated at t minus a times u of t minus a? So again, we're going to go back to the definition of the Laplace transform, the integral from 0 to infinity e to the negative st f of t minus a times u of t minus a dt. Okay. And just like before, I only have to worry about integrating from a to infinity. And on that interval, my u function is just 1. So this becomes the integral of e to the negative st f of t minus a dt. And now I can make a u substitution. So let's let u be t minus a. Then du is dt. And my integral becomes e to the negative s, but then t is just u plus a, so I put u plus a here, times f of u du. I have to change my limits of integration. So t equals a becomes u equals a minus a, which is 0. And as t goes to infinity, u is also going to go to infinity. Okay. Now from here, I can factor out an e to the negative as, and I have the integral from 0 to infinity of e to the negative su times f of u du. And then when we look at that integral, we should be able to recognize that as the Laplace transform of f. So we have e to the negative as times capital F of s. Okay, so 3 rules. Let's summarize what we just saw. So the Laplace transform of u of t minus a of s is e to the negative as over s. The Laplace transform of f of t minus a times u of t minus a of s is e to the negative as times capital F of s. And this one, we can reverse it, just write it in the other direction or with the other notation, and use it as a rule for an inverse Laplace transform. It says that the inverse Laplace transform of e to the negative as times capital F of s is, and the inverse is a function of t, is f of t minus a times u of t minus a. And then one more thing that's not separate from these, but you can derive it from these. A situation you may find yourself in is you want the Laplace transform of just g of t times u of t minus a. You don't naturally have a t minus a in there. right? But you could just use, well, you could define your f of t to use in the preceding rule as g of t plus a. And if you were to do that, then you would find that f of t minus a is g of t. And then we could write the right-hand side is then e to the negative as times the Laplace transform of g of t plus a evaluated at s. Okay, so I would say we've got this rule here. This one you're going to be using, and really the other two that are not boxed right now are they're equivalent, of course. You could use either one of them. In these lectures, I'll be thinking in these terms, using it this way. Okay, let's see what time I've got. Actually, maybe I didn't run a timer. Let me stop here and I'll make another part to this video.